So hello everyone. My name is Jianqi Hu, and I'm currently a postdoc in the Laboratory of Photonics and Quantum Measurement in the group of Tobias Kippenberg. So today I will basically give a brief introduction about the post-pumping and supercontinuum generations that are like relevant to the SOLIFEM training workshop. So I guess like in the last few days of the workshop, you have been very familiar with the current MicroCom generation. So basically what you need is a high Q microresonator, which you see in the middle here. And then you pump in with some kind of a high power CW light, which in the spectrum is basically a delta function. And then, I mean, in the time domain, like the pump in the cavity is actually these red lines. So it's a flat power like across the resonator. Then through some kind of nonlinear effect and also dispersion and also gain and loss in the cavity, you can generate as output broadband Soliton microcom. So instead of the original frequency, now you're generating new frequencies that actually have a second hyperbolic shape. So I mean the process you're very familiar with, like it's the double balance of anomalous dispersion and also nonlinearity, also parametric gain and loss from the system. And this type of system can be described by Logato-Laffer equation. Basically, the A here is the mean field in the cavity, and T here is the slow time, which like accumulates with the round trip, and phi here is known as like fast time that tells you the time like signals within the round trip, and then D2 is second order dispersion, and G is kind of nonlinearity, and kappa is the loss, and you can also detuning terms. And of course, you need to drive the system with the CW drive in this case. So this is like the Soliton generation with the CW light. And it has enabled many applications. Probably you heard already from the previous talks and also following the Gregor's talk. So there's many applications like dual-com spectroscopy, frequency synthesis, low noise microgeneration, and optical communications, and many others. And among these applications, a lot of like scenarios, it actually requires the Soliton spectrum to have a broad bandwidth and also with a low FSR, so that we can directly detect the bit node with a photodetector. So and why we need that? Because if our spectrum is like optic spanning, that means like the spectrum covers the whole octave, then you can basically take the one end of the spectrum. For example, I mean, this is a frequency axis, so you take some low frequency part of the spectrum and you double it with the second harmonic generation. And then you beat it with this part of the spectrum. So this way you can really retrieve the FCEO, which is like the FCEO of the comb. And in this way, I mean, if you stabilize the FCEO and also the repetition rate of the comb, then the whole comb can be stabilized. So so this is one of the goals of the Soliton microcom, such that it maybe it can be used for as a like tabletop frequency metrology system, just like this kind of system based on the like typical Morlock lasers that are commercialized right now. indeed, people are trying to going towards this direction, and for this talk, we're interested in like low repetition rate microcoms, but in this case, somehow the frequency spectrum can't be really broad to cover the octave. I mean, if you can see here, like these are kind of some state-of-the-art com coverage at the moment. So it can cover like 200 nanometers or 100 nanometers at a frequency grid of 10 gigahertz or 20 gigahertz, but it cannot really reach an octave with just a CW pumping. And I mean, the left-hand side, you see the spectrum. It looks nicely. This is sash square shape, but in fact, the process is actually suffers from very low energy efficiency. If you look at the right part of the slides, it actually have a very like very huge CW component that is present. So so that means your generated com lines are actually in a very low with very low powers. So I mean, certainly that is we want to improve the energy efficiency, and let's yes. So then there's also so the CW pumping, it suffers from the energy conversion efficiency. But another consideration is that, for example, if you really have a large cavity, so that because we're interested in small FSR comps, then like your cavities with the CW pumping, it could in principle support many number of solitons. So normally for soliton pumping, when you scan your laser through the resonance, at the beginning you will generate some kind of a modulation instability state, which is the thing you see here. And there are many pulses in the cavities. They're not soliton yet, but then if you further scan it, it could in principle like suddenly generate some kind of goes to this dissipative Kerr soliton state. But then the number of solitons inside the cavity or the energy inside the cavity drops a lot. Then I mean there is a large temperature change that these solitons will be gone, unfortunately. So what happens is, like, for example, we are like decreasing the laser frequency from blue to red. Then when I'm scanning, then initially I do my laser scan in this way, but then at some point that I can go to the soliton state, because when you're switching from the modulation stability to soliton state, the power drop a lot in the cavity, so that the cavity cools down immediately, the resonance shift a lot. So then the detuning condition changed completely. So then you go to the CW branch of your solutions, and basically there's no pulses in the cavity. So to circumvent these issues, people were using some kind of single sideband modulation to do the fast scanning, so that if you scan it fast enough that is faster than the thermal to take place, then you could eventually land to these places, these soliton states. But that requires some kind of like additional work from the experimental side. So this is just like a summary of the CW driven microcoms. So so the first thing is that, as I said, if it's a large cavity, then the overlap between the pump and the generated soliton actually are very small. So your pump is evenly distributed along the cavity, but for example, if you're generating just a single soliton, is just very say it's just like just takes a little part of the time. So most of the pump power is not utilized to pump the soliton. So, and this thing not only makes efficiency low, but also it will generate a lot of heat that makes the accessing of the soliton not being very reproducible and not very stable. And in this way, because the pump is like evenly distributed, you normally can excite many solitons, or I mean, of course you can do some trick to reduce the soliton number, but I mean the generated number of solitons is a bit uncontrolled in this case. Then if we think about it, the way to improve the system is to use, instead of a CW to pump the cavity, but you use some pulses to pump the cavity. So in this case, for example, if you can pump the cavity with some kind of pulses that are not even across the cavity round trip time, but some kind of have some short time windows, then in this way you can really improve the overlap of your pump and also the generated solitons. So this way it will increase the efficiency, and also it will also manage the thermal instability issues, because I mean now probably you have the similar peak power, but your average power is much lower compared to the CW pumping case. And because now also the pump is localized in time, and that actually only allows the soliton really being generated only in these time windows instead of being everywhere. So in this way, you can really control the number of the generated solitons to be like single soliton or low number of solitons. And yeah, that's basically kind of the advantages using post pumping. Yes. So how can we generate this kind of pumping process? So first of all, this pumping process need to be have a large FSR, because you need to match the FSR of your pump pulse to the FSR of the microring. You can do like not exactly matching, but normally it has to be, I mean, normally, but you have to be at least like harmonic or sub-harmonic of it, then you have the lines really going to these resonances. So a reliable way of generating this kind of like high repetition rate pulses is to use a electro-optic frequency comb. I mean, here is a sketch of the EO frequency comb setup. It's basically it's like doing modulation of the CW lasers. So you come in with the CW laser, then you're going through some cascaded like amplitude modulator and also phase modulators. You can generate electro-optic comb lines in the spectrum, and then you use a dispersion compensating module to compensate the chirp within the optical signal. Then you can really compress the pulse that makes the pulse used for pulse pumping. And this is a typical spectrum that generated from the EO frequency comb. I mean, it's really kind of a flat top and also kind of transform limited. And the EOCOM spectrum or EOCOM FSR is actually given by the IF clock rate, like the IF synthesizer you use to drive these modulators, and you can tune this frequency to really match your cavity FSRs. Yes. So the two essential components used for these EO frequency combs are one is phase modulator and the other one is intensity modulator. So if you drive the phase modulator with some kind of sinusoidal IF signals, it's basically described by the equation here. I mean, you have some optical carriers and you drive it with some kind of IF signals. I mean, you modulate the phase of your CW light. So, I mean, this equation, you can basically do some kind of Jacobi angle expansion, and you get in the spectrum many lines. So and these lines whose amplitude actually follows this Basel function of the first kind, and yeah, this is basically how phase modulator works. I mean, in the time domain, because you are doing phase modulation, if you detect the intensity, it's still kind of flat. But in this case, you're already generating sideband because you are phase modulated. Yes. And then for intensity modulator is nothing else but basically two phase modulators, but with some certain bias. So instead of being the phase modulation is like you're modulating the phase imaginary part exponential, but now then you're doing some cosine function of this with some bias. So basically, yeah, here you're also driving it with same I frequencies. You can also get some spectrum lines in the process. And in this case, of course, you will have some temporal modulations because it's an amplitude modulator or Mach-Zehnder modulator. You of course get some modulation in time also. So these are like basically two important ingredients for the EO frequency combs. And how does it really works? And the idea is actually really like proposed by Victor, the organizer or the PI of the workshop back to 2008. So he had this like proposal published in Optics Letters, which is lossless equalization of frequency comb. So I think the basic idea is that he actually gets the idea really from the not from the time frequency community, but from the space and like momentum kind of stuff. So we are very familiar with the working principle of lenses. For example, you come in with a collimated beams and with a lens, you can really focus it down. I mean, we take it as take it for granted, but actually this EO comb generating process is essentially the same as this spatial lens system, because in our case we call it a time lens. I mean, it's essentially the same as a spatial lens because we get this space-time duality. I mean, basically, because diffraction is similar to dispersion, and also, temporal modulation is also similar to spatial modulation. So that's why they have one-to-one correspondence, and this guarantees the working principle of like Hauss generation in time domain as well. So maybe I will just explain a little bit more about how spatial lens works. For example, you come in with kind of beams, then what a lens does is actually lens gives some quadratic phase while in the spatial domain, right? Then it means that if you look at your wave vector space, you actually have more components than the incoming beams after the lens. Then through the then you propagate through like a focal length, propagate through a focal length, through then this dispersion, diffraction effect really compress those wave vector components. So yeah, that's why it makes it a small focus. In the spatial domain, I mean, it's the same in the time domain. So if you come in with a CW light, you are kind of flat in the time domain. Then you do some pulse modulations, like amplitude modulations. You carve out some kind of pulses with the amplitude modulator. Then what you do is like you do a phase modulator. I mean, as I showed in the previous slides, we got 3 phase modulators. We really give it like a large quadratic phase in the time domain. And note that this quadratic phase will preserve the temporal shape because it's just phase modulation. But if you look at the spectrum, it really gets broadened a lot, right? It's the same. This phase modulator is like the spatial lens in the space domain. So it gives some quadratic phase in the time or spatial domains. Then with the dispersion, which is actually diffraction in space, that really can compress the quadratic phase in the spectrum to make it a short pulse. So that's why with this dispersion, dispersion, it gives kind of quadratic phase in the spectrum domain that can really compress down the pulses at the output. And at the output, you get almost transform limited pulses from the process. And then the system also have some time to frequency mapping kind of properties. So what you get, the output spectrum shape actually looks like your time, your temporal waveform when you input it. If you're going through this, if you're like in this large, like a Fourier limit. Yes, so this is how it works. So then I'll briefly talk about dispersion compensation. So as I said, like after the phase modulator, your pulse actually have a large like chirp, and you want to compress this. You want to cancel this chirp by putting some kind of dispersion compensating modules, which can be a spool of single mode fiber, or some dispersion compensating fibers, or even some chirp block gratings. And yeah, so the dispersion effect won't change your spectral shape because it's a process. You're giving some quadratic phase in the spectrum, but won't change your spectrum envelope shape. But indeed, it will compress pulse. And that's we use this kind of process for pulse pumping. And here is like some experimental setup in the lab. So basically, you come in with some kind of you come in with the RF signal. Then here is like RF splitters. You basically split these RF signals to different modulators. Then of course, for each of the modulator, you need to adjust their phase correct. So that's why we need phase shifters to adjust their relative phases. And also we will need RF amplifiers to really boost the RF signals, because modulators normally has quite high VPI and we want to have a large modulation index. Then that's why we need like these high power RF amplifiers. In this figure, you can basically see that here are like amplitude modulators and phase modulators. And also for many applications, it's ideal that we put some RF filters after the RF amplifiers to really get the RF frequency we want and like reduce the noise. So yeah, this is the experimental setup. And indeed, this using EOCOM pulses to drive microcavity and generate microcoms has been initially demonstrated by Tobias Herr, Scoop, and using a FP cavity of kind of like a silica fiber. It's an FP cavity, but essentially it's very similar to our traveling wave microresonators. And indeed, while you drive this EOCOM to this FP cavity, you can generate single soliton as the output. And the good thing with this system, as we described before, it will have higher efficiency. And also here the repetition rate is very low at 10 gigahertz. I think at the time is very challenging to achieve, because if you use CW pumping, the energy usage will be, the efficiency will be really, really low. So then, we're talking about the soliton generation, which is like a microresonator, but then we also have this like conventional soliton conventional supercontinuum generation is like you have kind of excite system with some kind of optical pulse strings. Then through just a single pass of the waveguide as the output through the nonlinearity, dispersion, and some other nonlinear effects, your spectrum will be broadened, but maybe in a more complex way. And in the case that if we have a very long cavity, then in this case will be kind of resident supercontinuum generation that, I mean, if you look at each round trip, it's kind of a long waveguide you propagated. So, which is, and we term it as resonant supercontinuum generation. So I will just briefly give an introduction about supercontinuum generation. So the first supercontinuum generation in fibers has been reported in 1972. So at the time, the supercontinuum is not that broad. It has something like 200 nanometers. Then it's fastly evolved, and then this supercontinuum generation technology really enables the Nobel Prize in 2005 for this optical frequency cone, because if you take a more log laser, the spectrum is not wide enough. Then through this broadening in this in the fibers through the supercontinuum generation, you can reach octave. Then once you reach octave, as I said before, then you can retrieve the FCEO and FREP, and you can really stabilize it, and then you can do metrology with these kind of supercontinuum or frequency comp sources. And then in around the 2015, I mean, people starting, or even a bit earlier, people starting to look at the supercontinuum generation in integrated waveguides, because the good thing with this platform, there are several. First thing that we can really do the dispersion engineering, which can be pretty difficult for fibers because fibers are drawn. And in integrated photonics, you can tailor your geometry of your waveguide to change a bit of dispersion. And the dispersion are very important for the nonlinear effects, particularly supercontinuum generation. Yes, and also in integrated photonics, the mode volume are more confined, so that fibers normally have a slightly larger like mode area, but in integrated photonics, you really squeeze the mode in a small mode area, and that really enhances nonlinearity as well, so that people were observing supercontinuum in mid-infrared, in visible, or even UV kind of stuff. And the supercontinuum generation is described by the generalized nonlinear Schrodinger equation. I mean, it's very similar to the Lugano-Lapper equation I showed in the first slide. But here, in this case, is like you don't get the external pump term, but you have the loss term, dispersion, and also nonlinearities. But of course, you get other nonlinear effects like Raman effects or self-stiffening. But I will not talk too much about it. If you're interested, you can refer to this literature for more details. So indeed, as I described before, we generate, we describe how to generate an EOCOM, and we can get a short pulse in the time domain, and we use this as a pump to the micro resonators. So in this lab, we did some experiment before, like we're using 14 gigahertz EOCOM to drive a 28 gigahertz silicon nitride micro resonators. So in this case, the COM FSR, the input COM FSR, and the cavity FSR is not the same, but it's like being subharmonic, like 1/2. So effectively, like every second line will be used to pump the solitons. So, but nevertheless, it still works. So if you look at it, like if it's low power, then we get kind of typical soliton shape as well. But if we're like pumping it with higher powers, we can see the COM spectrum is really broadened. And in this case, we also see some kind of dispersive wave being generated at the very far end. And in this case, the spectrum is pretty broad with such a small FSR grid. So, I mean, here is some kind of dispersion considerations. So, as I said, if it's for microcom generation, you need anomalous dispersion. So if you're anomalous dispersion, and I mean perfect anomalous dispersion, you get like perfect square shape in the spectrum domain, and you in the time domain you are like soliton sitting in some kind of CW background. But of course, your dispersion cannot be just purely quadratic, but in fact you will have some higher order dispersion terms. And for example, in this case, I mean, you can see that in the far end, the tail of this quadratic relation is compressed down, and then you have some zero dispersion wavelengths at the very far end, and you can see that the dispersed wave will be generated, or Cherenkov radiation will be generated as this zero dispersion wavelength that effectively change your spectrum of the soliton, and also small details of the soliton in the time domains. So indeed, with this pulse pumping, we can not only generate a single soliton, but also low number of solitons. But if you look at it, we can experimentally generate 1, 2, 3 solitons, and these solitons are very like closely spaced because they have to be in the range of the pump pulse. So that's why you see this large spectrum interference in the optical spectrum. And here, because we use, as I said, we use pulse to pump, there's less these thermal issues while we're using CW pumping. And here's the generation of solitons. With pulse pumping, you can basically use the piezo scanning instead of using some SSB techniques to really take care of the thermal effect. There's also some interesting noise properties of this resonant like supercontinuum generation. So in this case, if we are like soliton based in a cavity, it actually has better noise performance compared to just a single pass soliton generation, which is confirmed by the measurement here. So basically, there's some linear filtering effect, which is a cavity response, and also some nonlinear filtering effect, that is soliton generation, that purifies this comb lines, like the frequency comb lines in the resonant supercontinuum case. Yes. So we have been describing the soliton generation or pulse pumping, whatever, in the anomalous dispersion region, but pulse pumping can also drive normal dispersion microcom. So in normal dispersion is no longer the solitons, like, but in this case it's like called switching waves or platicons. So it's kind of more like squarish pulse in the time domain, and that's why, like in spectral domain, you see some kind of syncage functions in the spectrum. So with pulse pumping, we can also excite this kind of pulses, and indeed, it has been also shown in the experiment, like in normal dispersions. With pulse pumping, we can also excite these spectrums, and it's indeed correspond to the simulation. And in this case, because we have very flat dispersion, so that the spectrum is extended to very far end.
What is the difference between pump and pump?
I think is probably just the generated, like the pump power difference. Yeah. Yeah. So, I mean, I was talking about anomalous dispersion and normal dispersion, and there's also, I mean, a few years ago, like Miles noticed that there is also like zero dispersion solitons. I mean, here's the zero dispersion is not really zero dispersion, but it more tells about when the second order dispersion kind of vanishes, and then the higher order dispersion takes over. Like, so, I mean, the next one is third order dispersion. So in this graph, we can see that, I mean, the x-axis is second order dispersion, and the y-axis is third order dispersion. And when you have different second or third order dispersion, your Soliton solutions or like stable solutions can be of different shape. I mean, in the very left end is like the typical Soliton waveform, and in the very right hand is like this switching wave or platicon as shown before. Then when you're then the nice thing here is like you can really see the switching from the soliton to the switching waves. So when the second order dispersion kind of vanishes, then there is kind of transitioning from this soliton shape to the switching waves with an increasing number of these kind of solitons. Then eventually it will evolve to this switching wave shaped. And here is a simulation showing like with different D2 and D3 how it changes the spectrum and time domain. And the left, this figure that basically is showing the real and imaginary part of the time waveform, so that you can see. I mean, now it's like really zero dispersion, and now it's more approaching to the anomalous dispersion. So it's getting more and more like a single soliton. So we can wait and see. So two solitons, and then now will become like a single soliton. Then we have some kind of oscillatory tails, which tells you actually that's third order dispersion. And then it will, yeah, it evolves. And okay. So now it's like approaching more to this switching wave. You can see in the time domain the number of these solitons increases, then make it connect and make it kind of squarish pulse in the time domain. And this is towards normal dispersion right now. Okay, so so indeed, in the experiments, we have been generating kind of this type of solitons. So we were taking a sample that really have zero dispersions, and people were observing solitons with different sub-soliton numbers. And in this case, the generation efficiency is quite high also, and in a small FSR grade, and almost octave, but not here yet, but almost. And that's it. Thank you for listening. And any questions? Yes.
The animation you showed before, what are the sectors that with the dashed line?
This one?
The one, yeah, in the circle. The one on the right.
The one on the right is switching wave. Left is anomalous, like soliton, anomalous dispersion. I mean, it's basically D2 and D3 ratio. I mean, here is like D2 vanishes, then you have like positive
I understand that part. What are the dashed lines that go?
I think the dashed lines like defines different boundaries when it goes from one to, we can have a look. I mean, it's kind of some boundaries, like switching from, now it's still kind of, you can call it switching wave. Then it will goes to this kind of zero dispersion Soliton regime is like these Soliton numbers, like 5, 4, 3, 2, 1 kind of, yeah, stuff. Yeah, it's basically, I mean, this region is orange, covered by orange colors, and they have different numbers of these zero dispersion Soliton. Okay, any other questions? Okay. Okay, thank you.